Hello, everyone. Welcome to this workshop, Productizing with Kubeflow Orchestration with Feast in GCP. My name is Faraz, and I'm one of the co-organizers at MLOps. It's my pleasure to introduce Aniruddha Choudhury. He is the senior data scientist at Publicis Sapient with over 4 years of experience in IT. He has also worked at one of the largest banks in the world, Wells Fargo. His experience in IT is in providing AI developmental solutions. He is also very passionate about data science and data engineering, complex solutions in machine learning and deep learning. So over to you for the workshop.
So I think good morning or good afternoon from wherever you are. So today we'll be going to talk about production as a feature store in Kubeflow Orchestration with Feast, and the entire platform we'll be going to build in Google Cloud platform, right? So what are the agenda or session we'll be going to cover? One is the technology, the concepts, and why feature store, what is feature store requires, and how we build the feature store, and how to build the batch or stream data, and we're going through the production grade, building the Kubeflow pipeline from scratch, and how to serve the endpoint for a prediction for a particular use case we're going to see. So I pasted the link so you guys can have a look into that. I gave you 2 parts. I have set up of Kubeflow 1.3 and the Feast in your cloud platform. You should have a billing account to deploy Kubeflow or install Kubeflow in Kubernetes. So these are the things which people might require as a prerequisite before you start. So coming to the session. So these are the touch base components which we'll be going to use in our entire 1.5 hour session in this workshop. And I'll going to touch each of these topics, what we are using and what are the things we're going to cover. Now, why we need feature store? Now, this is the first question which will come up in why we need feature store. So as there is a lot of data across our industry, and we might have known, right, the data is a new oil, and there are a lot of data scientists, data engineer, ML engineer have been discovering the fragmented ideas from the data, right? Now let's imagine a situation, right? Some data scientist, one project got started, right? And some data scientist is working on some sort of a use case, and some use case can be regression or classification or any sort of a modeling or deep learning, right? So and if you have a team of 3 or 4 people, they spend a lot of time in building the data pipeline, building the analytics behind the data consistency, and they'll build the data training or serving. Now, some data scientists might pre-process the data with respect to their analytical skill, and some data scientists might do other sort of scaling or transformation of the data. So there might be a deduplication of data. Some might have done some sort of a scaling, some might have different scaling in your data before training. So there is a lot of lack of efforts in data deduplication. Now, what about the ML engineer, right? So ML engineer or data engineer, they manages the copies of data in a fragmented data structures. So they maintains the multiple data. So the data, the data scientists which have built the particular set of data and they pre-process the data engineer will maintain the data for the production rate system, right? Now, each data scientist will have their own analysis on the particular data before training, and they will save that particular set of data in particular storage or any sort of a NoSQL databases. Now that comes into a lot of challenge in maintaining the data structures or maintaining the data for training, right? So that is the where feature stores comes into the picture, where a consistency will be there between your training or serving, and it will ease the life for both data scientist or ML engineer or across business analyst or across the entire project level, right? Now let's give an example how AI/ML workflow without a feature store, it will work. Let's take a use case one, right? A data scientist will start their work of journey by a data collection or data analysis, and then feature engineering and model training, right? And the ML data engineer, which will take the raw data and will do the feature engineering and do the model serving and prediction. So there is a lot of inconsistency in the first use case. Now, the second data scientist, again, he have done some data collection and data analysis and feature engineering on the same sort of data. So there is a deduplication of feature efforts. So let's take an example. A data scientist who have 3 years experience in e-commerce domain, he might not have an equal amount of experience to a 10-year person who have working in the e-commerce domain. Let's say someone working in a Walmart, right? He have a lot of business or domain knowledge. So at that point of time, the feature engineering, what the 10-year person or the 3-year person might do, there is a lot of gap. So a data scientist might work in various domains, but the domain perspective will come into the picture, right? So the feature engineering is directly proportional to your domain knowledge, right? With respect to that. So if two data scientists are working on the same data, right? So there will be a lot of deduplication of feature engineering. Some might inconsistent on top of that. So there is a lot of high maintenance of your data for your training or your production grade system when you will do a serving to your application in the backend. So how the picture will look in with feature store, right? Now let's say I have a centralized repository where all my feature engineering are published there, right? Now a data scientist will do a particular set of steps like data collection, data analysis, your feature engineering, or your model pre-processing steps, you can say, and whatever statistical analysis they want to do prior to model training, they can do on top of that. Now we will publish the particular features in feature store, right? Now a scenario one is like a same feed data can be used in various use cases. Let's take an example for supply chain management, right? A supply chain management, a data scientist had published some sort of a features for, let's say, for a retail customer centric data, and he have transformed the particular set of data and he have published it to a particular feature store. Now the same data can be used for a scenario one and scenario B. So the first data scientist who is working in a particular centric of use case is like a regression model, right? On top of that. So he will use this particular data and he will use accordingly into for a regression, and he can build the centralized repository data pre-processing, which has been done previously on the left side, and he can use it for the regression. So the another training scenario is like, let's say another data scientist working on some classification problem. Is the customer is a good customer or on top of or a bad customer, or he can what sort of analysis on the he can do on the use case. Now he'll get a centralized repository data. He can pull the data which is already pre-processed, already feature engineered, and he can pull the data with respect to any domain knowledge, and he can build that particular model on top of multiple algorithms. Either it's a deep learning, or it's a traditional machine learning, or a statistical model, right? So these will ease the efforts of feature engineering. These will ease the efforts of your data scientists, which don't have any domain knowledge on top of that, and they will get the experience on top of how to use those particular features for the different use case, right? So these will connect the bridge between your feature engineering to production grade and it will maintain a consistency between your production training and production serving, right? Now, what is feature store and what is feature store with Feast, right? So we'll be talking about the Feast. So Feast is open source packages which has been developed by the Gojek team, right? And they have made it open source. Now, what is feature store, right? As we are talking about how the feature store can ease the life of our data scientist or ML engineer or data engineer, right? So Feast is it will solve a lot of challenges in production grade system, then, right? It will maintain a consistency on top of that. Now there can be a various ingestion of data. Either you want to push your real streaming data or you want to push your batch streaming data. So in ingestion of data, there are a lot of tools you are there specific to particular cloud. Either you can have a real streaming data for Apache Kafka, or you can have a streaming data for Kinesis in AWS, right? And for batch data, you can put it into a Redis cluster, or you can have a memory store in Google Storage. So these will manage your storage and of a streaming and batch data. So you can have both streaming and batch data, whatever you have pre-processed prior to that, right? So there is, and regardless of the environment, there will be standardized features across all the domain specific use case or across the industry, which will have a specific standard features, which will be encountered for the further training and modeling, right? And suppose I have published my features and I can share to the other data scientists who is there, right? And I can share it across with my central repository. Hey, look what this is my features, right, which have been pre-processed, and this is the central repository of my feature store. You can take care of this feature store and you can build your machine learning algorithm on top of that. So there will be enough use of references, of semantic references, or same features. And the data consistency, and there is a lot of similar consistency which will be maintained in both training and both serving. And low latency is there, right? So low latency, which will be your point of time of correct features. Now it in the model training, we'll get a lot of features which will be a point of time who have the latest features which is been pushed into a central repository, and we can validate our tracking, our performance, our model, and our all the features into a feature store. So these are the 5 components which has been mainly are there in feature store, and it will be covering I will be covering all of these topics. So it contains the transformation, the storage, and the serving, and the registry, right? So these are the major 5 components of feature store, which will be your key pipeline to encounter or to build the entire production grid system. So let's talk about the 5 components what we have. Now here the serving is on top of a Redis cluster or Redis data structure, right? So the serving is a low latency which will fast quickly give you the data, right, for a prediction endpoint. So and it will store the feature with respect to a latest time values, and it will maintain a very high latency, low latency data structures for your predictions, right? And the API can be a low latency database. So suppose I have deployed a particular Redis cluster in a Google Cloud platform, and I have an API working of an application. So there is the time of getting the particular data at there is a low latency is there. So that means that the reduce of the time. So with respect to low milliseconds, I can get the data for in a production grade system in particular application for the prediction, right? So it will save a lot of time of traffic into that. Now, what sort of transformation we have? So transformation is an orchestrated process which will process your data, and it will turn the feature values. Now the new featured values is like, suppose I have an initial raw data, I have pre-processed the data. Now I will have to have built a schema on top of that. Now there are 3 types of transformation. Either you have a batch transformation, either you have a streaming transformation, either you have an on-demand transformation. So batch transformation, a specific set of a transformation of a, let's say I have a 1 million records, I will transform that records, and I will have a batch transformation schema or pipeline. On top of that, I have a streaming transformation. So whatever the incoming data will come on a Kafka or Kinesis, I can have a particular streaming transformation on top of that. Next, I have a feature monitoring, right? So it will monitor all the utilization and capacities in Grafana or Prometheus. We can integrate in our Kubernetes on our cloud platform. Now, what these features will do? These features will time to time will monitor the matrices which will be generated for my feature store, and it will generate the health of the application, how the model is behaving, what feature is impacting my model prediction, and is there any decay in the model, or how the existing observation of the particular is working in a particular production state. Now coming to that, what are the features majorly we will be taking care, right? So there are a lot of features in Feast, right? So I think we can take care of the availability, we can take of the latency report, we can take of the utilization staleness, and we can take the latency rates also with serving throughput layer. Now, what about the registry? Now, what are the features you are transforming, right? What are the features you are transforming? What are the features you are pushing? So there is a central registry. That central registry will work as a standardized feature definition of metadata or a schema for or the point of truth for all the features which you have pushed. So right. So this registry you can say as a key to your feature. Let's say I have a domain data. Let's say I have an e-commerce data, and I have transformed the data. I provide a name for the particular transformation. I have pushed it in my registry, and it will centralize particular registry. In that registry, it will be stored across a particular key value. So that value is the particular data transformation for my e-commerce data, and I can pass this registry across my fellow peers, my other teammates, and they can use this registry for their particular model building and all. Now, how the backend is working now? So the snapshot, so the offline, there are the 2 parts. One is the online storage, and then is the offline storage. So the offline is they can store the data in S3 bucket, in BigQuery, Snowflake, and Redshift, right? Now, what about the online storage? Online storage is a low latency storage, right? Which will be using for your prediction in production grade system. Now this we can majorly we are using right now here Redis, or you can use an AWS cluster. We can use a DynamoDB or Cassandra on top of that. So that will be a low latency. So these are the 5 components of a modern feature store. Now, how the life cycle of a feast works, right? So I get a domain-based data. I will do my feature engineering of analytical EDA or pre-processing, some graphs or statistics or some probability score or distribution or outliers or whatever things I will do on the top of analytics. Once I've done the analytics, I will jump to my feature engineering data transformation stuff, right? So I will transform my data with respect to your scaling or with respect to your particular set of business use case, or any you are adding features. You can add features or extra features which will add your variance or your mean or with respect to your data or domain. Now you transform the data. What next? Now you have to plug in your to the FIS bridge, right? Once you plug in, your all the data has been stored into a centralized repository, and that data can be used for modeling. So in this perspective, I have all the data pre-processed, and only I have to load that particular data into particular data frame or any SQL or any cloud data frame in Python. All I need to train the model with respect to different algorithms. So that stage is, I can tell, as a pre-engineered features. That means I have already trained or feature engineer is over. I don't need to do anything during the model training production stage. Now there is another part is a very semi feature. Now you have done some domain-based, you got a domain-based data. I got my analytics. I have done my feature engineering on top of that, and after that I'm doing my data transformation on my production system. Now the incoming data, whatever is coming, let's say I have a computer vision images there, right? I have to scale it, or I have to descale the image or the noise or reduction on the incoming data. So I can do some pre-processing on the serving layer, right? And that serving layer, the data will be hit into the particular serving endpoint. So this scenario will come into your semi pre-processed, semi engineered features. So these two steps, I think we maintain in the life cycle of this during our entire journey. So let's take a scenario, how feature store works. So this is a churn modeling, right? And on top of that, I have a features of customers, I have a features of transaction, I have a features of payments, I have a features of tech support. Now, all these features have a key, or you can say a customer ID or payment ID with respect to that. Now, a point of truth is like with respect to a date timestamp, right? At what date the record is generated, I can join or merge all the features into a master feature store, right? Now, what this will do entirely is a pipeline which will build the multiple sources of data, and with respect to your payment ID, with respect to your date timestamp, which point of customer ID the record is. So it will merge the data with respect to your particular key or date timestamp. A date timestamp which will match the nearest date timestamp, which will match the particular row or records a point of thing. Now, how I'll use this particular data or feature store for training and prediction. Now, similarly, I have merged the data in a particular centralized repository. This is the repository where my centralized feature store data is present with a particular registry name. And that particular registry name can be a customer ID with respect to particular date timestamp where your particular records has been created. Next, after that, this will be used for your training purpose, and this will be used on top of your particular training in production grade. Next, you have a predictions also. So features which we can be used for prediction for incoming future data. Now I can have a particular customer ID or records of incoming data, which will be used on top of your prediction layer, right? And these features to be filled as a point, and it can be pulled from your central registry, and you can push your storage into a central registry of a data, and we can pull it there for your prediction. Now, what are the myths behind the scenario which are not covering in Feast? So Feast is not a workflow scheduler, is not an Airflow or DAX scheduler which will automate your process. It's not a Kubeflow orchestrator which will have a scheduler on top of that. It is not a data warehouse. It's not covering any Hive or Snowflake, or it's not in that process. And it is not a data discovery of data hub or a data MS system, and it will not build a pipeline on top of that. The Feast doesn't provide any pipeline building, and it will not automate your feature engineering. So you have to do your feature engineering. It's not like a feature engineering. With the feature engineering steps, we are publishing into feature store code registry, right? And it is not a data version control like DBC, right? Or CVC, or for a Git control or a model versioning or drift and outlet check or model decay, right? And we don't have support here the model serving. Now, either you can use Sheldon or Bento, right? Or case serving. And it will not replace the collaboration across the team. So all the data scientists have to come up and do the particular business domain use case on each other. So what are the benefits and features too, right? So I have a centralized repository or a central registry of my particular set of domain data. I can share it across all the teammates, and it will reduce the duplication efforts across the teams, right? With respect to a person who have a 2 years experience, who don't have a domain knowledge, and with respect to a person who have 5 years experience with respect to domain knowledge. So it will ease the effort of a particular newcomer to your team who don't have too much of a domain knowledge on top of that. Slowly and gradually, he can understand the feature analytics behind your from your center repository so that he can build a model on top of that. So it will reduce the time of efforts across the industries or the companies who are working in multiple use cases. What is the decoupling? Now the decoupling is, right, your feature engineering is a separate track, your modeling is a separate track. So you can maintain a particular feature engineering and modeling separately. So it is a highly decoupled thing. Now registry. Now this registry is a point of truth where you're storing your data with respect to your features, the features which you have transformed. So it will have a center repository. Some might have working in a particular domain. So and you can have a multiple domain into a separate cloud environment in a registry in feature store. And you can have a different, you can pull the particular registry name and to pull out particular historical data or your online data. And it maintains a consistency across your team. So this consistency will be with a similar functionality across your training and serving, right? And it supports ML frameworks also. The data which you pull, it supports your ML frameworks, or either it's a deep learning framework, PyTorch frameworks, or a MXNet or U framework. And you can have a real-time features access. And once you have the repository access or registry access, you can get it. Now, how feature store works? Now, we have seen what and why we need feature store. Now, how feature store works, right? How it will works internally and how it's supposed to the production grade systems and how we build that thing. Now, on a high level, right, your feature store contains the data sources. Your data source either can be S3 bucket in AWS, either can be a GCP, Google Cloud Storage, or you can have your Kafka source data, right? So you can have a various data sources, and you can have a feature store on top of a middle layer, and that middle layer contains some Kafka, Redis, or BigQuery as a low latency high data storage or data structure. And you can retrieve those data or features for a training and serving model. Now, how this works? Now, you have a project or representation. This project will be a central feature set. That particular feature set will be used for different entities and features. So entities is just like a key of particular data. I have a key, let's say driver ID or customer ID, and the features are the number of columns or of a data, or the features which is representing particular data table, right? So, and the both can be connected into a particular feature sets. The feature sets will connect particular row of data entity with respect to features, and both this will be stored into a particular set of projects. So on that projects, the entire feature registry can be stored. Now, how the operational flow of a feature store works. So let's take this break into 3 parts. Either you have a sources, either you have a administration, and you have a stores, right? Now, let's say I have a data scientist or an analyst, right? They will first do some pre-processing steps. They will do some pre-processing steps, right? And this pre-processing step will store your feature sets and stores and will publish into a feature code. So this feature code, your central administrator place where all the feature internal is working, right? I'll publish my registry of particular feature sets or columns or data into a feature code. Now this feature code will publish some sort of a metadata and fetch metadata, right? Now this feature code, once you register, let's say I'm giving XYZ registry name and all the features of a data, I'm publishing it to a feature ingestion. Now this ingestion will be doing a Spark job on the backend. So this Spark job or a client will push the data into a broker, right? And that data can come from any other sources, either it's a S3 bucket or is a GCS bucket, you can store it. So that can save as a subscribe as a feature row in particular message broker, right? Next, after that, you save the data, some sort of data as a historical data, and you can save the data as a parquet file in a particular historical store, and that historical store as a schema, it can be can be shared across GCS or S3 on another bucket. And similarly, I have another store have a low latency store. So this low latency store will have a particular Redis cluster, so that data can be pulled out quickly. Now, once you register the data into your feature core and ingest the data, you save the data, right? Next, you have a feature retrieval, how you retrieve the data. Now, there are two ways to retrieval. Either you get a historical data for your training, or you can have a low latency data from via Redis, which will do your prediction endpoint. So these low latency and underlying low latency store with particular Redis will give the data with a sort of milliseconds of or respect to that for a prediction. Now you can get two ways. Either you register your data and you retrieve your data. Once you register, you can retrieve the data for a particular central repository or central structure. Now, how are we going to build that things end to end right now in our this demo, right? We'll ingest the data into let's say I have a data of 30K. Now or 1 million records. I'll save the data in any storage. Now your data can be any storage. I post it in my GCS bucket. Now you'll do your feature engine steps. Your feature engine steps after done, you will push the data in the batch ingestion. Once you're done, you build your Kubeflow pipeline with your historical data, right? Once after that, you take the serving layer and you can build the serving layer on top of that, and you can monitor the metrics, right? You can monitor the metrics of the model via Grafana Knative, right? Where you can see the model traffic, or you can see the model performance, how the model is behaving, what is the load, what are the auto scaling things. Then you can automate the entire process. You can automate the entire process by Airflow DAG, or you can have a Kubeflow DAG to do the entire steps, right? And once after that, you will build the production grid system into end-to-end flow. Once you have an entire pipeline to build, let's say I have a domain specific use case, and I have done my pre-processing feature engineering steps, and now I can build an entire automation on top of that with your DVC or with your Airflow to scheduler to maintain the ingestion, and you can build a pipeline in Kubeflow to train the model simultaneously and deploy the model weights, and you can track the model in a model DVC or model monitoring to which model weight or model output you can deploy it for a production. And in a low latency Redis, you can connect it to your serving layer where you can quickly predict the output of that, right? Now, how internally we are going to build this thing. The entire things, the stack has been deployed. The Kubeflow stack has been deployed in Kubernetes engine. So you can deploy the Kubernetes with respect to Kubeflow on top of any cloud, right? So I'm using Google Cloud. So I'm using this particular Kubeflow stack of 1.3 in my cloud. Now, how my data works. So my data is working in my raw data is present in data cloud storage. This is bucket. So I pull the data. I've done some pre-processing steps, right? And once after that, I'll start an ingestion of Spark job. Now that Spark job registry will be used by SDK. So you can have a Feast Python SDK or Java SDK or Go SDK. You can use this in the SDK to ingest your data or feature services to both historical or online storage. Now this Spark job will run on the backend once for your retrieving the historical data. And that historical data as a data frame, you can convert that parquet file to a data frame, and you can train the particular model, either it's a TensorFlow, PyTorch on top of that. Once you're done, right, you have another part, your online Redis store, which have a low latency real-time features. So you quickly can call this online Redis store from Feast, and you can hit the particular endpoint and cave serving, and you can build the cave serving up. Once after that, you can have a get or prediction request on that, right? So now, once you use it, right, so there is a Feast SDK. That Feast SDK will have a client, or will have a core or a Feast job service, which we're going to see in the notebook, which how we are using that particular thing. Let's go to the hands-on lab. Okay. So I pasted a link, right? I think because it takes a time to install all this stuff, right? So I think you can set up your Kubeflow environment on GCP, right? Or you can have all the steps has been mentioned here, or you can have the particular set of installation link of your Kubeflow in here. You can go directly to the Kubeflow official documentation. Once after that, you deploy your Kubernetes cluster. It will take some time it will take some, I think, 30 minutes to come up with your HTTPS domain-based load balancer. or ingress gateway. So once after that, you will deploy your Kubeflow cluster. You can deploy the features stored first on top of connecting to the cluster. Once you have to connect to the cluster on Kubernetes, once after that, you install the requirements. Then you have to expose a Redis to a load balancer. So this is like an external IP which you are exposing to the world of a Kubernetes. On top of that, you have to expose your particular patch of a Kafka also, which is on the top of your Kubernetes. And you can install a data proc cluster in your Google Cloud Storage, and you can take the minimum bare grade of 2 GB of your machine of a particular data proc compute engine, and you can start the particular thing. Once after that, you can install the particular Grafana or Prometheus for monitoring, which you're going to use for model matrices or feast matrices on top of that, right? So, and what are the notebooks I'm going to show you here, or everything is presented here. So you can, once after that, you can, once after this particular workshop, you can go ahead and have a look into this. Cool. So this is the particular documentation of Kubeflow. Whoever is comfortable to particular cloud, they can go to the particular docs, and they can, they can particular start the particular environment and can deploy the particular environment on top of a Kubeflow, right? But I highly recommend you can go start with a Azure or Google Cloud or AWS. Right? Do have a lot of things. Challenges are there in the, because Kubeflow 1.3 is coming, and a few of the bugs are there. So the Kubeflow community, people are working on top of that. Okay, good. So let's take a step back, right? Now I'll be using a particular data set, which is a Kaggle data set and is open source of NYC taxi regression or classification, but I converted it into a classification problem with respect to the profit of a particular data, right? So first, few integration is there. I have post all the codes there. You can have a look into that later on. So there are two parts. One is your data is coming from your particular cloud storage. So there are two tables are there. One is a fare table, the taxi fare table, which will be covering the how much amount of data or your taxi for a particular driver, or how many passenger has been done, he has been traveled, and what is the fare amount. And the table is there with respect to what particular date timestamp, and what is the peak of date timestamp, what is the key with respect to the longitude, latitude, and drop of longitude, right? So these are the feature values I have on top of that. Now what next? I'll check what are the missing values are there. I will do a specific feature engineering on top of that. I'll be using a particular set of things where I'll check the missing values or analytics behind it, right? I'll drop some ambiguous data, which will be some NaN values on that. Now, next, I'll check the data type or data type, because the data type is very important when you're registering your feature store into Feast. So you have to see carefully what are the data types we'll be using, what are the data types we'll be publishing, and that data types should match your data frame and your feature registry. Next, you have to convert your data frame date time to a date particular set of time, right? Because that's an object. Now I have to convert it into particular date time. Then I'll be checking what is the profit check. Now the fair amount is there. I think is a $2, $10. I give a threshold of $8, right? So $8 is my profit for a particular day, or particular day for a particular driver. Now that threshold can classify into particular matrices of 0 and 1, and that matrix has been converted into a good profitable day of driving, or a particular less not profit, right? Next, I will converting this particular, I'll be adding a feature. Now I'll be adding a particular feature is a distance. Now the distance is a very important feature, might come because a driver is dropping from one location to other location, and or with that respect, the distance might cover, right? The distance might have a proportional to your particular feature. Let's say fair, right? For a short distance, I have a feature have high money, right? Or a high token of amount. So on top of that, these features might give a lot of impact in my feature, or you can say model performance on like that. So I've added extra feature on top of that. Next, what next? So I'll be covering the skew check. Now the skew check is like I'll be plotting some of the plot distribution with respect to skew check, and this skew check will be done some QQ plot and your mu sigma on a normalization fit. And so on top of that, this skewness will tell, okay, in this particular data frame, my external columns contain 3.8, 5 point and positive skewness. My data is okay, it's distributed. Let's try to distribute it more or scale it more or reduce the skewness on my data. So once I've done it right, I'll get my data. So my skewness is reduced to some sort of extent, right? Now I will do some log transformation on my data. So, or I'll do some power transformation on top of my data. That power transformation will consider U Johnson methods, right? Which we will be covering on based on the particular shape. I will transform the data of a particular thing, and I will reduce the skewness. Then I will check the skewness. Okay, my skewness now reduced to 0.03, right? And now it reduced to quite a bit of a distributed, normal distributed data. Now my data is well normal distributed. I'm not doing a lot of feature transformation, feature engineering with respect to time, right? So now let's say I have my feature engineering data. Now I have transformed the data. Now I have to save the artifacts. Now I have my feature data. You can save the data artifacts in your local storage, and you can store the feature in artifacts in GCS or any storage. Once after that, I'm saving the data here in my local only, right? So these are the features are there. So once after these features will be consumed by feature store or feature engineering or my feature feast, right, on top of that. So once after that, right, I will be using the geoplots. Now I'll be just checking a casual geoplots, how the distribution of your particular set of pickup locations is working. I can see that highly dense cloud of a particular distribution is presented here, right? So might be if we can want to do a lot of analytics behind it, we can go ahead with the latitude and longitude. We can add a lot of features or dynamic features on top of that to add the model performance on that, right? So once you have done the particular feature engineering steps, once I have my feature steps, right? So what next? So I have my feature steps. I'll jump to my feature engineering feature store notebook. So this is the notebook which I'll be reiterating again. This is the architecture which will be reiterating again, which we'll be using here. So first I will load all the steps. What are the features or attributes or import libraries are there? So what are the first three things are there? One is a project, one is a entities, one is the feature table and features. The project, entities, feature table, features. This is the high level flow from your projects to entities to feature table to features, right? Now, first thing what you have to do when you come to here, once you deploy your Kubernetes cluster, Kubeflow, right? You have to expose your IP and you have to run kubectl get SVC. Once you run this, right? So I have my Kubernetes. So kubectl get SVC, or you can say kubectl get pods. So these pods will give, I have deployed my Kubeflow, right? These pods are my deployment. Yep. So I have my deployment. So all the pods are ready right now. All the pods are ready right now, and I'm working on these pods. Now these pods, I can expose it also by getting the services. So this services already exposed. Once you have what you have to do, you get the IP for a particular set of problem. So this is the IP address of this Kafka, or this is the IP address of a Redis cluster, right? Once you grab it, after that, you have to copy this sort of attributes. You have to copy the Redis Kafka and paste it below here. You have to copy the project ID, your project ID of your particular set of a cloud, which project ID you are using. So which project ID you are using, then your Dataproc cluster name, the Dataproc cluster name which you have deployed. So I have my cluster Dataproc. Take some time. So I have my Dataproc cluster is running. So you have to grab the name here. Let's open, I think. Yeah. So you have to grab your Dataproc cluster name and the GCS bucket, your cloud storage bucket, at which bucket you want to save your data or parquet file, right? So I have my Dataproc cluster running, and it's running in the US East 1B or US East 1 region, and there are the 2 worker nodes, and this is your cloud storage bucket. So this bucket you have to copy it, and that particular bucket will come to your Spark storage location. Now all these are your environment variables for a Feast SDK. Now I have to first initiate my Feast SDK as either writing Python or Java or any language, right? You have to initiate your Feast SDK on top of that, and these are the attributes first you have to fill, right? Once you've done it, your environment variables is ready. You can create a bucket in GCS bucket. You can create a random bucket on a Google Cloud Storage. Once you create the bucket, you have to initiate the class. So I have wrote a class. This class will initiate the environment. I am using Dataproc environment. So so you can have your other environments, either if you're using ECR or EMR. In AWS, Dataproc replica is EMR. And in particular Kubernetes also, you can have inside Kubernetes, local Kubernetes Spark operator. You can like Kubernetes K8s also. So you can get all the documentation of Feast SDK in the Feast website, where all the SDK is there. So once I initiate the Dataproc, so I'll be using Dataproc. So my entire environment variables will be Dataproc. Once I given this particular data service name, and this is my namespace. So in Kubernetes, this is a namespace which we are using. I'm deployed into namespace, particular my default namespace, and this is the port where it is exposed internally into particular Kubeflow. So, and this is the Parquet format, how the data will be stored, Parquet format. Now, how your historical data, which will be retrieval for your online historical training for training features at particular stage. Now, let's say I have my storage at GS, this path, and after the / historical, this is my historical data will be saved there. Then this is my Redis port, a host, and this is my Redis port, and this is my serving URL, and these are all not exposed, these are internal to your Kubernetes cluster. Once after that, you provide the Spark launcher. This Spark launcher is dynamic. You can provide Kubernetes K8s, or you can provide Dataproc or with respect to yours. Once after that, you have again you initiate your Kafka brokers. So this Kafka broker, you can have your IP address of the whatever the expo you will do the exposed in your Kubernetes cluster. You can paste it here. Once after that, you initiate the particular clients in environment. I can check the environments here. So these are the environments which are initiated in my particular notebook, right? And I'll be using going forward. Now this is the Feast SDK or client. So this client will be consuming all the particular attributes of environment here, right? Now the pre-processed data, the data which we have pre-processed last notebook, I'll be importing those notebooks again here. Now those data is feature engineered data, and those data is completely feature engineered, right? Now I'll be using those particular set of data for my next purpose. Now I've loaded this particular fare data and trip tables. Now first I'll change date time. When you take it, it will be object. So all the date time and created. So what is the meaning of created here? Created is the particular set of action or data row which has been created at the particular time. And pickup date time is the occurrence of the event. So the occurrence of the event is made. So going forward, we will going to see the importance of these two particular set of columns, the pickup date time or created. So the any event timestamp of your data, it can be anything. You can take care of your pickup date time. You can provide your date time, whatever is there originally, but you can have to create a date time which is you are creating at the particular set of feature engine. Let's say I am on June, or a particular set of time, I am doing a particular feature engine for the data. I'm providing a column for this particular 1 million records and create it. So that is the point of event occurrence which you have done, and that is the point of event which has been done earlier and which was present earlier, right? Once after that, I transform my data into a data, my date time, and I'm checking the date time. Okay, or these are the particular set of float and date time, and the data types are there for my two tables, and this will be going to handy for the next feature registry, right? Now I'll be initiating few the class, right? So this class will be containing two things. So as I mentioned, right, there will be a set of features which will be three things. One is the entity, another is features. So the entity will be a key of a particular data frame, let's say customer ID or driver ID or any other ID, right? So this ID, I'm declaring it here. So this ID will contain a particular int64, right? And this particular set of functions will talk about which column, about which what data type and what labeling should I give. So feature will cover some labels. Now let's say the labels, I can provide dynamic labels. Okay, this particular column or feature it will be required for production environment, and I can give some text or dynamic text. Okay, this is longitude column, and this will be used in production. So I can hit some labels in my features. right? Once you do it, you can create features for both the tables. So I have 7 columns. I have created a 7 features labeling for all the 7 columns, and for my other column, other table, I have 3 columns. I have created 3 feature labels, right? Once after that, this is the particular features labeling will be done by this table. Now this will automatically take care of what data type your original data frame is there, and it will be taking, okay, if this is in 64, so the feature will take this feature is a particular SDK of Feast. Now this feature will consume 2 things. One is attribute name, what name you should give to particular column. So that should be saved into a feature registry. You can provide XYZ, what are the column name in there? Let's say longitude. So that column name will go here. And what is the value type? So that type is int64. So you have to declare the value data type, which will be stored into a data in your feature registry. Once after that, you provide the labels which I've created earlier, that will be transformed and will be given here, right? So these labels, I can anyone using any sort of features registry, they can see, okay, this features is being using for this production, this features is being using for dev, and this features will be using for your test environment, right? So each features labeling have a different meaningful things, right? Now again, you can have a float 64 according to your data types. All the features will be registered in your registry. Now once I declare it, similarly for the table 2, or I will have another feature for my table 2, I have to declare 2 features. So first I will check which columns I should take, right? These are the columns from my trip details tables I should take for the feature registry. Now first I will declare the feature entities, right? So these feature entities will call this particular class, right? It will call this particular class, initiate the class, and it triggers 2 things. One is the data frame. What is the data frame you are going to push? What is the entity column, the key column? Which columns you require to push into feature registry, and what is the registry name? And you should provide a unique name for your registry so that it can be identified for your feature purpose for modeling or serving, right? So that name should be very important. We should declare as a unique global name. Let's say I am declaring trip statistics. I want to provide a name, unique name trip statistics, and I provide an entity driver ID, right? And these are the column names I'm providing. And these are the trip details data frame. So this data frame is already present here. The first step I'll do, I'll declare the entity. Now what is entity? An entity is a domain-based object or which can be stored as a recognizable concept, or you can say persons, place, entity, events, right? A particular set of data must have a particular key or entity which will be, we can track it with a particular set of a row, have some meaning for particular records, right? So first we have to declare the entity for driver ID. So my driver ID will go for my entity here. Now if I go up, how the entity looks. First, you have to declare the entity. So below it was actually feature. For feature, other columns, it will feature. For entity, you have to declare entity. Similarly, you have to provide a name. What is the entity name? You can provide a column name, and you provide some description. Okay. Once you provide the description, you can declare the value type. What is the in value type? You can provide some labels. So this entity will be used in production, or you can provide some text. Okay, these are the things are there. Once you're done, right? So you have to declare your feature table. So I first data frame, I am declaring it for my feature fares. Now I'll be declaring few things. One is that these are the feature table registry. So trip statistics is my feature table name, the master name, and this table contains all the columns. So these are independent as a entity feature tables, which will be covering all the features, and it will track all the features, and it's a dynamic object. And once after that, I will declare the fare statistics table. So I will declare my second table. I will deploy the, I will again register the second table. This is my another data frame. I'm providing the entity name, and these are the columns. This is the second table columns, and passing the column names. I'm providing a particular set of unique name of fare tables. Once after that, I declare completing my feature entity and declaration. So once I have completing my declaration of feature table or feature columns and what sort of features I should take, then I will go for schema declaration. So you have to, now you have declared the features. Now where you are saving it? I am saving it in a Google Cloud Storage. You can provide the name of your local also. I mean your Jupyter Notebook local. But if you want to provide the name for a Google Cloud Storage or S3 bucket, you can provide the bucket. So I already have declared the environment variables earlier, right? So I can see this is my test data. Now I go so first for the first feature table, for my first feature table, right? So the trip entity. So these are the features. So I have already declared the features. Trip entity is my features. So this is the entity of my data. This is the master key of my data. So how I declare the feature table? So this feature table is a batch data, right? So this is a batch source. First, you have to provide a unique name. So the unique name is trip statistics. What is the entity? The entity is a driver ID, so which is unique, right? Then after that, features. So these are the features which we'll be publishing here. Trip entity is nothing but these are these columns, right? These features declaration. Once after that, one event timestamp is there. So this event timestamp is that what particular column is your event is created or generated records. On top of that, when you created the records, and you can save the data in a parquet format. So you can have different format. You can have a look. So and this is the URI where you want to save your data. I want to save my parquet format data in here, right? In this cloud storage, this particular location, and this will partition my data with respect to date. Now, once you save the data, let's say I am saving the data, I'll show that how it looks in the GCS bucket. Again, I have to declare the similar feature table for my second table, right? This is my second table where I am declaring the same thing. So once you declare your feature tables, what is the next? Now, and the next step is the core component. I'm talking about the 5 components. The next 5 components, the first component will come feature registry. So I have to register my features into a feature store administrator. Now, this feast client, the feast client which I have declared earlier, right? So this feast client will apply, feast client dot apply will save your entity. So this entity is nothing but the driver entity for the first driver entity, right? And the trip statistics and the fare statistics. So the feature table which you have declared, the feature table which we have declared, you have to apply them. So this will run the feature steps for your client registry. So once you're done, how it looks, the feature table declaration. Now each feature table has a proper schema. So my entity endpoint is unique endpoint is driver ID. And what are the features I'm providing? For longitude, okay, this is double. The value type is double, or you can be int or float also. What are the labels I'm providing? This is the label. This depth feature longitude distance means longitude distance for the trips of city, right? And providing other tags also, you can provide tags. Now for other columns, you can provide your tags, right? And this is the batch source data information. So this batch source data information we're talking about, okay, this is the particular location where your data will be saved for your historical retrieval of a data. And when the metadata has been created, this is the timestamp. Similarly, for other featured table, this is for other table data frame. This is the particular set of attributes or schema which has been generated. Now you have registered your feature into your feature registry. Now the next step is to ingestion. Now you have to push your data or table, you can say, to your feature table or you say in a feature registry administrator. Let's say I have a 30K rows, right? I'm already I have done it because it will take some time. So you can take 30 rows also. You can streamline 30 rows. The client which I've in the earlier initiated on the first during the first environment variables, I have to ingest my trip statistics. This trip statistics is nothing but your this feature table. So this feature table will work as an ingestion with respect to data. Now the data is table, right? So this table is my data frame, and this is my feature table, feature schema, or you can say the feature table, which is stored as an object. So this will store the information of what are the data types and all. So it will internally it will run a particular administrator feature core or metadata, right? And it will ingest the data into a feature batch source, right? Similarly, for the two tables, I have ingested it. Now this data, once you ingest it, it will be stored into your feature registry, and it will be present into your cloud storage bucket also, and it will save the data in this format as a parquet format as a date, because with respect to date, it will save the data with respect to date in a parquet format, right? So once after that, I can see the feature table stats, how the stats will look for a particular client and how it's going to see. Now, the next step is like you have pushed your data to feature registry, right? You pushed your data to feature client. The next step is a batch source ingestion. Now this batch source ingestion will take the feature values and it will ingest the feature values with a particular set of time. Let's say I want to ingest online, offline to online ingestion with a low latency. The low latency online stores will be used for serving, right? This feature ingestion will be used for serving. So later on, this one, the things which you have ingested, this we're going to see how we are going to use this in our Kubeflow pipeline, right? So once you ingest the data for offline to online ingestion for a low latency for feature, and this backend will be work as a Redis data structure, and we'll be going to see how we are going to retrieve the data from that particular thing. Now, once you do it right, you can populate the online with Feast SDK. So this SDK has some method of start offline to online ingestion, and this is a particular table, or you can say the feature table, which will publish the data. And this is a time zone max or minimum. I want my feature data to be published from 2009, 18 records to 11 records. So this will publish your data to online ingestion. And once you run it, this will run a Spark job. So this will run a Spark job on the backend. So if I run it, let's make sure that, let's say I am running it. So let me refresh it. So these are the Spark job which already was running, and already I've run it before this. Okay, now let's come. So this will publish the data to your online storage for Redis data structure, right? Which you'll be using for your feature serving and that. Now the next one you can do your real-time streaming ingestion with Kafka, right? Okay, yep. So see, this two will running because I am running two tables. So this is where you are doing your client feature. Spark job is running on the back end on your Spark cluster. Now you can have a heavy compute engine on top of that to run the particular Spark job, so that you can quickly can do it, have it do transaction of millions or billions of records on top of that, right? So once you do that, there's another technique where you can another way to ingest the streaming job. So this will come to the transformation of component, the component which I was talking on the previous 5 components. This is the transformation component where you're streaming a batch or your semi-batch data, you're publishing it. Now you will be using Confluent Kafka or your Avro or whatever the Kafka topics you want to use, right? So first I've created some utility function. One is which will create the Kafka topic, right? And the Kafka topic IP address, which I have showed you, you can pull it down from here and you can take this Kafka topic IP and you can build your Kafka topics or list, right? And this is a list. This function will create list your all the Kafka topics, and this will publish your all the consumers. And you have to create a Avro, Avro schema for that, so that the records can be stored, and this initialization you can do. So once after that, I'm pulling out my Kafka. I'm checking what are the topics are there. Okay, these are the topics are there, right? I can initialize my Kafka topic. First, I have to initialize this class. I'm initializing this class. Once after that, I can create a topic. You can provide your name, what with respect to your one, and it will create a topic. Once you create a topic, you can list the topics with this admin client also. Okay, these are the topics are there with 3 partitions and 1 partitions, and you can save it. Now the next step is you have to define your Avro schema for Kafka source. Now this Kafka source is another attribute of Feast or feature engineering on Feast client, right? So this Kafka source will take event timestamp pickup date time. Okay, this will take the created timestamp and the bootstrap servers, the IP address of your Kafka, you have to provide it here, and the topic which you have created earlier, you have to provide the topic. And this is the Avro format schema, the data frame which is there. You have to provide the data frame attributes and type in a similar schema structure here. And what are the particular data frame will look for a pickup date time also, you have to provide that particular thing also. Now this will generate a unique name with trip statistics, right? You have to provide that particular name. Once after that, you provide client.apply, right? Once you provide the client.apply, your Feast will start applying that particular Kafka. And once you do that, this will run on top of Spark job. So this stream tree statistics Kafka source or Kafka client, you have to run a particular stream, start stream to online ingestion. Now once you want to ingest your local data or streaming data to your online ingestion in Redis data structure, so this will also run a particular, if I run this, so this will also trigger a particular Spark job on the backend. and this Spark job will continuously running. So because you have to stop it, because this is a Kafka, as this Kafka will be your real streaming data. So once you do that, let's take I'm doing some ingestion of 10,000 rows or 10K rows on top of that. I'm putting a records, a particular record of a peak of date time. I'm publishing, changing the date time with UTC format, right? Once you do that, you call the class here of Avro format. So this will publish our data into a producer of a Kafka topic. It will first write in a data writer, and you can change into a bytes object. Then it will encode that particular object, and it will write the particular object as a record, and it will publish to a Kafka producer, and it will produce this. You can send the topic with respect to the whatever value is there. So once you do that, where am I? Once you do that, now my data is present in a data structure which is our Redis data structure, which is high low latency, right? Now let's say I want to retrieve 100 rows with some sort of a driver ID. I want to retrieve the data for this 100 rows or 20 samples of driver ID, right? And the table which you have, the feature table from which you have declared earlier. Let's say for this feature table, trip statistics, this is the columns I want. These are the columns I want. Or I can dynamically reduce the table also, right? But I'm providing, okay, for this unique name trip statistics, I need these columns. Now, so in this feature, client get online features. So this client get online features will retrieve the online features, right, which you have published into feature table in data structures. It will quickly will retrieve the data, and it will publish the data here, right? Now, what you next to do, you have to cancel the job. You have to cancel the job. So this will take some time. Now, if you see here, so this is canceling because this is a Kafka. So because this will be real-time data, you have to cancel the job, or it will be continuously running if you don't stop it. Now, once you publish the data, let's say this is the data for my master table or trip statistics data frame. So for my trip statistics data frame, I published all the data, and these are the data which I got for the online streaming data, and which has been very fast and quickly low latency. Now, once after that, similarly, I will do the next step for my fair data ingestion. I will publish the data with Kafka source, and again, I will run the Spark job. I'll check the status for the Spark job, and again, I will publish the 50 rows or 1000 rows according to your wish. Again, I want to retrieve some sort of features, and this is the features I want to retrieve, and this is my table. So this will retrieve your features once you publish in your data structures, right? In Redis data structures. Now, next, we have saved our data into feature table, and you have saved what next? And I have to build the model training purpose, right? And let's say I have to build an entity key and entity timestamp. Now, what is the entity key? Now, this entity key and entity timestamp is the occurrence of a particular event which has been occurred particular frame of time and particular records. Let's say I want to save all the records, 30K records of my entity key and driver stream, which will be using for Kubeflow training, right? And this records of driver ID and event timestamp, which will try to pull out from my feature store table, and the latest record will be pulled, and it will create a data frame, right? Now, let's say I want to create the saving the schema. So this schema will save all the which table. I have already two feature table. One is feature statistics, one is trip statistics. I have merged it, so I've saved it as a JSON. And this JSON has been saved it into a particular format in my GCS bucket, so that I can use these two things. One is my driver ID, another is my feature JSON for my training purpose for modeling. So once after that, let me go to. So once after that, how to build the Kubeflow pipeline. So once you start the Kubeflow, you have to break down the Kubeflow pipeline into three parts: your feature ingestion, your hyperparameter tuning, your training, and your serving. Let's say my first part will contain three things. In these three things, we'll cover your Docker file, your, pardon, I think let me delete this one, your Python file, whatever the Python file you are taking care, right? And your recommend.txt file. So these are recommend.txt file, which contains all the libraries which you want to install in the Docker container. Once you do that, right? So I think you can use the latest, everything is there in the Git. So you can take the particular feature file, you can declare which is the entry point, Python cmd run. Once after that, you have to declare all the inputs. So this is how. So first I'll declare the inputs. So what is my entry point? My entry point, this this Python particular Docker image, or you can say Python file is this. Now, I said I have to click options. What are the inputs you are passing from external community or external factors, right? So your GCP project, what is the project ID you are working? Your target column, what are the target column for your prediction? And where your data is stored, the feature driver ID, the entity which I've saved just now, right? And my JSON. So these two will be used here. Once after that, this will be input, and it will trigger the environment. So this environment is nothing but the environment which you were using earlier. So this you have to reiterate the same to so the Feast client can take those environment variables and again retrieve the historical data. So the online offline storage data. Once you do that, you retrieve the features JSON file, the particular skip feature table name, and you particularly load the data in a JSON and can read the particular ID. So this is the ID, whatever you are taking care. Once after that, this is the event timestamp which will be getting history. So this is the client. Now this client will consume all the attributes or environment variables which we have declared here, right? Once after that, client.get historical features. So this is the function of feature SDK, which will retrieve your historical features. So these are the feature names, right? You have to provide the feature names, the names which you have declared, the two tables. From the two tables, what are the names are there? Entity source is nothing but your entities, right? So these are the entities. The just now I've showed the entities and their timestamp, the particular driver ID and timestamp which have been occurred, which I have stored in GCS bucket. I pulled it out. Let's say 30K rows I'm taking, and your staging bucket, the bucket where you save the GCS bucket where you save the data. And this is the config. You just have to. This is a pre-config stage. Once after that, this you can load it into a particular data frame, right? It will take some time and it will run a Spark job on the backend. Again, a data cluster in run a Spark job, right? So it will load your data, whatever the features you published. This command will load your data and you can convert to a particular data frame, right? And we have a utility functions. So let's say my data is in a GCS bucket. So you can run a GCS bucket. Let's say my bucket is in S3 bucket. It will return a data frame. If you have Azure blob storage, it will return a blob storage data. And if you are in a local, it will read a data of a path. So it will return a path of your data where the data is stored. So this data will be, we will read it here. So this is my empty data frame, and this will read the particular data frame, and I will drop the empty columns. Again, I will declare my target column of my for my training. So this is my target columns, and this is my column which I don't need for your training. I am dropping target and driver ID ambient timestamp. I'll do some sort of scaling if it's required, or you can skip it. Now I have to split my data into X train and Y train, right? And you dump the things into your PVC. Now we are using Kubernetes PVC and Kubeflow, which is your internal PVC or persistent storage volume, which will save your data during the training phase, right? It will save the data during training phase only. Now this is an individual component, and this component will dump this particular set of data you have trained, whatever the data you have retrieved from Feast client SDK of historical features, and you save the data. Once after that, I'll go to the hyperparameter tuning, and you can have your framework, either is a deep learning framework or any framework, right? Again, the entry point will be this, where you want to save your TensorFlow logs, your epochs, your batch size, right? Again, you declare some sort of variables. Again, you put your, you can load your data, whatever you saved in the previous step. So the data which you saved in a PVC in a previous step, you have to load it again here, right? So that it can be reusable into here. So this also contains some sort of a Docker file and your entry point of a Python file and all the requirements and the training file. Once after that, you train your data, you declare your hyperparameter tuning, and you can have accuracy, you can have a matrices in TensorFlow. Now I'm using traditional just a TensorFlow hyperparameter tuning. You can have a RayTune or any other framework, you can use it. Or Cative is there in Kubeflow, we have Cative, you can integrate Cative also. Now once you don't do it right, you publish your data and you can say which other models is the best, you can save the results onto that, right? And this is the TensorFlow logs which you can publish, and you have to save your TensorFlow storage upload. Now you can load the model artifacts in GCS bucket also. We can save the TensorFlow logs and upload. So this storage Python file will upload your data to Google Cloud Storage or any directory or any bucket where you want to save it. You can have your own storage file for AWS or any other things. Once you do that, you can save the model artifacts and you can save the model artifacts. So once you train it right, I'll go to the serving evaluator part. Here I will evaluate the particular set of things. So again, the entry point will be a click.com option, right? So this will this will contains all the options which you will be taking. You can again load the model outputs, and again you train it, reiterate, and you save your particular model, which will be used for your serving purpose. So I have saved the model in Google Cloud Storage bucket, right? I'm saving the model in particular GCS path. So this is the path where I'm saving the model, which I'll be using for my particular model prediction. So once I store it, my model, I can have your confusion metrics and all, everything I'll be there in your Kubeflow dashboard, right? So once you do it, the three parts is done on top of your feature ingestion, hyperparameter, and training. Now what next? So the next step will come to the serving part. So this is Kave serving. So underlying is a Kave serving or wrapper on top of your Sheldon or a Flask also, or a fast API. You can use your own APIs also. You can build a fast API and can deploy it into a Kubernetes cluster by exposing a particular thing, or you can use a Kave serving, which is very high low latency and very model tracking, model versioning is very good, and we can track the auto scaling things in here in Kave serving. I'll show that. So Kave serving, this I'm using a Kave serving template of custom model, right? So I'm taking, because as I want to see how the custom model, you can have your any other models for TensorFlow or deep learning, other frameworks, or sklearn, any Allied GBM or XGBoost. So what it will do, so this is the Docker file, which will be entry file of your serving endpoint. So you can have a serving endpoint Python layer, and you can have your all the Flask, Sheldon core, or what are the requirements is there. You can load it here, and this is my Python file which I will be taking. Now first I'll declare the environment variables. So let me open it side by side. So a few things. This is the template of Kave serving. So this Kave serving, you can deploy it with apply -f to feature your your framework. And once it will do two things. Once it will load the model, and you have to declare these two functions with respect to anything. These two functions should be there. First step, it will load the models. So let's say I've saved the model in this particular path. So I'm giving an environment variables, right? GCS bucket, whatever the bucket you are saving it. So this bucket will store the data. It will load the model of Keras model here, right? Once you save it, right? This is the environment variables. I'm pulling it, right? And this is initiating the variable. Now the two things. One is that this Sheldon core serving, and this serving name should be same when you're deploying it, because it will try to see which inference you deployed it. So these two names should always be same, and the namespace where you're deploying it. Let's say I'm deploying it X, and you're deployed it, and your inference is in Y, so it will fail. So you have to deploy the namespace in a particular name only. So let's say my name is Aniruddha Choudhury. I am deploying in my namespace Aniruddha.Choudhury. I'll show the namespace how it works. And once after that, first you have to load the model. So the first initially it will load the model here. Then your incoming data, let's imagine I have a JSON incoming data. These are the particular features. Let's say take a one row of particular features. I'm publishing it, and that instances will come to your incoming. You first have to scale it, a bit of a scaling, and you can convert in this scaling data into a data frame, and this request.instances will take the particular key of a data, and it will reshape the data. You can have a model to predict, and I give a threshold of 45 probability, or you can have your own probability, or you can do any pre-processed, either is image data, or you can do any sort of things like computer vision data or NLP, or you can do any other serving frameworks. Once after that, you can return the predictions, whatever is there, right? The similar things is there. This is the Kave serving template which you have to use, and you have to provide your namespace. You have to provide your GCR container. Now you have to build the Docker images actually. Now you have to build the Docker images. All the Docker images you can build it for each step. For each folder you can build it like from here. I've pasted the link. Docker.build. You have to push the image. That push image will return a gcr.io registry name. So this registry, similarly for serving also, we have to save it, and I'm publishing it in the GCR registry into a project. You have to provide your particular project name, whatever you are working, your project name, and you have to provide your dynamic name of your serving Docker image, and you have to provide your environment variables. Once you do that, once you deploy that, I think let me step back once. I'll go to the pipeline, how we build the pipeline. So once I get all the Docker images and entry point, I'll go to the pipeline, how we should build the pipeline. So how to build a Kubeflow pipeline. So the Kubeflow pipeline works on a DSL or DAC operator on backend, right? And it will generate a YML file, right? Now, what are the things? I have 3 folders, right? I showed 3 folders. You have to provide the 3 Docker images for all the things. and the entry point of all the features of the particular Python file. The dot click option, you have to provide the name, where is the staging bucket, what is the target, what is the data ID, what is the data features, and you have to provide similarly other features, attributes as the input to your model building or pipeline building. And you will have your serving layer also, serving what is the serving name. I want to save in namespace Kubeflow, and this is my serving step, and where you are save to your model. Now first I have to create a PVC. So this is a dynamic PVC which will create a 1 GB of dynamic PVC which will be attached during pipeline training. Once after that, there is a DSL container of DSL operator which will take the Docker image. So this is the Docker image. You have to provide the Docker image which you will be building on the steps. Once you do that, you have to provide an entry endpoint. This is the feature store service. So this Docker image of this particular Python file will be providing this entry point, and we have to provide this entry point here. And what are the attributes that you have to provide it dynamically. So these attributes, whatever is there in the Python file, we can show it here. Once after that, you have to attach the p volume with VOP, whatever the name convention you want to give, to MNT. So MNT is the folder path, slash MNT is the folder path where you're creating the volume and you're attaching the volume here. Once after that, you can have it for similarly for training, your evaluation, right? The next step is your case serving. The template which you have showed, I have showed it in the YML format. You have to transform it into a JSON format, and you have to provide the namespace. Let's say I provided my namespace Aniruddha Choudhury. You can provide your name, and you have to provide your Docker image name, and you have to provide your path of your Google Cloud Storage bucket name where your model is saved. You can substitute it, or you can directly hard code it. Once you do it, it will return a DSL resource op which will serve the model, your deployment name. This will load the JSON here. And what is the action? Action is you have to apply the Docker, your serving endpoint. Once after that, these are the steps, right? So these steps are connected here. First, I have one thing I missed. First, I have load this particular PVC. I have to give VOP.volume. Now this is my next step. I have to attach p volume feature step, feature store step dot p volume. So this will operate after this, right? Again, for this one, you have to provide training step. This will operate after this. Similarly for this, I have to provide the DAG operator. This will operate after evaluation step. Once after that, you have to declare a zip file. So it will return a zip file here. So it will return a zip file. You can download the zip file, or you can provide an API to upload it also. So once you download this zip file, let me go to the pipelines. Then I have to upload it like here. I go to the Kubeflow pipeline dashboard. Now I have to load it from a local file, wherever it is there, right? In which directory your file. Once you do that, I've already uploaded it. The pipeline look like this. So the pipeline look like this. So this is a PVC, this is a feature store, and this is a step for all the features connected. Once after that, I have to create a run. So this create run, you have to choose a particular version experiment, which experiment you want to create. Let's say I want to take an experiment. So under experiment, you can create a multiple runs in Kubeflow. So in Kubeflow, we can have a multiple experiment. Let's say I have 10 data scientists there. They are maintaining their individual experiment. Under individual experiment, you can have a multiple runs also, right? So once after that, you can have your populate all the automatic features or attributes or parameters which we have shown in the pipeline. So these parameters as a default will populate into your Kubeflow dashboard, central dashboard, and you can manipulate it according to your needs. You can delete it or whatever you want to do it. Then you have to start the pipeline, right? So once you start the pipeline, so let me create a run. So let me just create a default run. So to start the pipeline, so all the run details will come here. So you'll have a run pipeline. So first it will create the PVC. The min will it come? Let me show the other one. So under this experiment, I have two runs, right? One is running, already I've run it. So already it took 20 minutes for running the pipeline. You can have a CPU underline. If you have heavy data or you want to pre-process training, you can attach a GPU and CPU of a node pool into the backend to a particular pod into your Kubernetes, right? And once you do that, it will save the logs. You can have your logs. As this logs is, I've run it earlier. The logs are not showing, right? So let me go it. Cool. I think till that open, I think let me jump to the other topic. So once you train it, right, it will save your model artifacts, your model storage bucket into a cloud storage bucket in GCP bucket. Then after that, it directly can save the model and serve it directly in one step. You feature store your training and you can tag, and you can have schedule it, or you can have a pipeline to build that thing. You can pre-process it, and you can have a automatic automation production CI/CD pipeline, which will trigger these things into your Git or Kubeflow orchestrator, and you can deploy it, run it from anywhere, right? So once you do that, right, the next topic is like how to see the pipeline model pipeline online prediction. Now, how this works? You have published your data to a Spark cluster, and you published your data to Redis, right? And now you'll have your inference endpoint to a backend application. So we have deployed the Kave serving, right? Now my Kave serving is running. Now I will kubectl get inference service minus n is a namespace of mine. You can provide your one. My namespace is running, my Kave serving is running, right? You can describe it with kubectl describe inference. You can have to provide this name, and you can provide the namespace. So this will contain all the details. It's consuming CPU of 1 and 2 GB. You can increase the CPU according to the resource limit, whatever you want. If you have a cheap high model or very heavy machine model, you can push it according to your wish. So we have deployed the model. So already it's running. Let's see how to inference the predictions. So few things again, you have to initiate the class of your feed, right? So once you do it, there are two scenarios. One is to retrieve the historical features. So first, the two things which we required in training also we have done it. First, you take the particular data, put the feature table. We have two feature table, feature statistics and trip statistics, and these are the entities of data frame which you took. Now you have to run the historical features which you have run it in entirely in our pipeline. Again, this will run a Spark job, and it will retrieve a particular data. Once after that, you can have a status. We can see the Spark job. It's the data pro cluster Spark job is completed. Then you can have a prediction endpoint on top of that. You can grab a particular set of data, right? And you can have a prediction function. So this function will take this request.post URL, the URL which you want to hit, and the data. So let's say I took this data as a JSON, and this is the header. This is the header function you have to host. And this is the cookies. As cookies not required, you can internal, because I'm using internal DNS in Kubernetes. I'm not exposing internal outside things. So I'm internally using DNS. So in Kubernetes, it provides internal DNS. How the host looks like, the serving model name. The serving model, let's say my model name is Sheldon Serving. The name which you will provide in the YAML file, it will be have to provide here, and the namespace. So my name is Aniruddha Choudhury. I can provide my name, and rest everything is same. So these dynamic variables you have to publish here, right? And you keep it, keep the host, keep the headers, right? And just request this post. You can publish your URL. You can provide your data and JSON.dumps. You have to provide the dictionary should be JSON.dumps. You can provide your headers, and this will return the profit of driver, right? And this we can integrate it in the UI or even UI application, backend application. We can do this. Now, next is the scenario two is an online Redis, which will be low latency data structures, which will track the data. Now, I have a set of sample of data. I need 20 driver Redis data. Client.get online features will take the data. So this is the data which will reduce the or take the data. Now, once after that, let me run it. I think so it retrieved the data. My bad, I think I missed one thing. So it will so this will run a Spark job on the backend. So it will take some time, but it will run a Spark job again to retrieve the data. Now, once I have done it, you have to hit the particular URL. It will give the prediction. Now, again, you the same retrieval you can do with the online Redis. Your feast client.get features. You can retrieve the data. So I think once it runs the Spark, again you can hit the particular URL with a particular set of data and you can predict it here, right? So once you do that, so this will trigger a Prometheus, or we have to see the monitoring system. Now in our Kubernetes, we can deploy a monitoring system which is already running in my pod local 1990, right? So this monitoring will go to redirect to my Knative serving in Grafana. So this Grafana will come as a Knative serving, which your model tracking, your model serving endpoint. So as I am not hitting the endpoint, let it run. I think it will return the spike. So how many traffic, how many people are attaching clicking on the particular endpoint, and you can see the traffic, how it works. Now it is straightened because I'm not hitting the endpoint or the input of your particular thing. Let me try to do that. Let me take it. Till the time it runs. Okay, it will take time to complete that. In the meantime, I'll just talk about this one. So it will take all your namespace. So this is the namespace where I have deployed my Kave serving, and this is the model which you are serving endpoint. And you can have your session, or you can have your responses time, your model predictions, your response volume on your traffic and your succession rates. And you can see, is there any breakage of a model output or not? Next to that, once you've done your feature store, your model Kave serving track management, you can have a Prometheus on top of that. So this is a very advanced matrices which you'll be seeing. So I have already deployed a pod, and I have already told the steps. So this pod is connected in local 1990. So this 1990 is my Prometheus server. So I have, once you go there, it will open redirect to this page. So you see there are a lot of model matrices which is running on top of your Kubernetes on your feast. So you can, let's say I'm feast code total, right? So this code total, I have to just execute it, and you can attach it to a particular graph. So you can see for the last 1 hour, let me take, let's say for 6 hours, how the things are working, right? So I can have my feast gRPC request count also, which will talk about what are the latency reports, which features are decaying, what is the model release, right? And once you do that, you can add this features or Prometheus for all, for the model tracking or matrices of feature store into Grafana. And those Grafana can be, we can build multiple dashboards, and we can track it, and we can track our model graphs, and your feature engineering or your feature latency buckets, and you can have your own model management, or you can say feature store things. So this way you can track all the Prometheus and all the reports which you want to pull from feature store matrices. How are you saving it? What is the latency, and what are the pods? How is it working? What is the memory you are using, right? Let me take another example also. You can play around with this. What are the 2-day matrices? You can show the matrices. Okay, what is the report? What is the pod report? Is it failing where? What is the distribution time with latency with respect to time? And you can stack it also. What is the stack? And you can add this particular graph to your Grafana also, where you can track it. Now here also you can do a lot of things. So already I have few. So already I have my pods are running. So you can talk, it will talk about which pod you are. Let's say I'm taking any pod, you can take your pod, and what is the CPU consumption. So this is just a bit of a dashboard which you can create on your own in Grafana, and you can track your model matrices. I hope I am covered. I think that's cool. Yep. I think this is the entire journey of your feature store to your Kubeflow pipeline, to your serving and model matrices, to your building the dashboards, your serving and Dockerizing things, and your entire structures of your Kubeflow to feature store. Thank you. Do you have any questions, guys?
So, what's your name?
My name's Pooja. Meeting out now because her parents, because she has to. Her parents are going out in meetings, so just
Okay. You be careful with that iPad. If you drop it onto the pavement, it's going to break.
Yep, for us, want to take it?
Hey, yeah. Thank you so much for the walkthrough. I'm just seeing if there's any questions in the chat.
Can I ask a question?
Yeah, go ahead.
Yeah, Aniruddha, see, this is open source thing, right? Feature store. So
Yep.
if cloud is providing any kind of feature store, so like, can you compare, like, I think AWS is providing feature store. So what are the benefits if we go for cloud, or if we use feature store, like what are the benefits?
So in terms of cloud, different cloud have different sort of pricing management, right? Now, if you want to build your feature store in your organization, you can have to maintain a single cluster where you can run a single machine and you can maintain a lot of things. But if you want to use a managed services from AWS or any Tecton or the pricing comes up, right? The competitor, whoever the pricing management is there, some might have a different pricing strategy or managed services. You can have a drag and drop, or you want to build your own feature store in your own company. You can do that on your own, right? So I think a lot of companies are building their own feature stores and they're using some managed services also. Just completely up to the organization how they want to take the call and the team what comfortable they are. Either they want to use the managed services or they want to use the open source stack and can build that things on top of a lot of UI things on top of that.
Okay, yeah, that's it. Thank you.
Aniruddha, in which case we can use scale instead of writing a pipeline?
Anyone else have any questions?
Someone is talking, I think, bit loud. Can you be loud? I think I'm not able to hear.
One question that I had, Aniruddha, did you run your Kubeflow from Azure workspace?
No,
Like, can we do that?
no. You mentioned is just like did I tried it or is just like now whatever I'm running is the same for this
No,
one?
both. I mean, did you run from Azure workspace, or can we do that as like host everything on Google
Yes.
and from Azure?
Yeah, Kubeflow stack you can deploy it anywhere. I think because I've done it in Azure also, I've done it in AWS also, I've done it GCP also. But
Can we store the data in GCP and run Kubeflow stack on Azure and access the data which is on GCP?
You can have your service accounts, right? Either in AWS service tokens. You can have to initiate the tokens to access that particular bucket, and you can store it anywhere in block storage or.
Yeah, Anirudh, another question. Are you familiar with the scale feature which is providing in minikf? We can write pipe.
Yep, that is minikf, right? And that's like a drag and drop. I think by the Josh.
Yeah.
I think Josh is the vice president of the community, and I think I was the community. The Kale is just an automation tool, right, which will drag and drop the things in it. But on high complexity, if you go to the very higher complexity machine learning thing, then the complexity will break there. So it depends on the team. Again, I will say usually in my team, I try to different use case. The customers have different things, right? So that perspective we have to maintain it different because some clients might come up with, okay, I want to put it in Azure and minikf obviously present in multiple clouds, but their requirements is like, okay, you want to take a Kubeflow stack or you want to take depth stack. That's again comes to the pricing strategy. We can have Kale also, but the complexity is think on the complexity perspective and company perspective also.
My question is, can we use that feature as like production grade pipelines?
Yeah, we can use. I usually don't use too much, but
when we go for production, we usually write a code, right? So how the production system works with code, but will in company will they entertain to use that KL kind of thing? So
yep, KL will come with a managed service, right? I mean, if you would go to the marketplace, it will come with the pricing strategy. You have to some 300 or something. Now it depends on the company. They want to invest some time to minikf and they want to Aricato and they have to invest money on that. Now again, or you want to build your own platform and you want to start everything from scratch. So we
Okay.
can use it. It depends on us what to use.
Oh, yeah. Thanks.
I have a question.
Yep.
So is that true? You need to gonna ingest all the data also into the feature store.
Sorry, come again.
So the feature store will hold all the data. Is that true?
Mm-hmm.
But that means,
Yes,
let's
yes.
say the source is for us is using the S3, right? So which means we'll have two copies. S3 has a copy and the feature store has a copy.
Yep. So it works like this, right? It's like a repository where you're storing the data, right? It's not storing the data. I mean, it's on the back end, you are managing the data and the snapshot of your data is in S3 or a bucket or any bucket. So that bucket, you can pull it into Redis data structure. So that Redis data structure is containing all the data for online storage. But for historical retrieval, you need to run a Spark job, and that Spark job will communicate to your S3 bucket or other bucket where you can retrieve the data from. So that bucket have to store it. I mean, you have to store your data to somewhere, right? Either S3 or a block storage or any other thing. This is not a structured column SQL database or something like that. So this is like a registry where your data is storing in somewhere in your S3 bucket. You're connected with a Spark job and you're pulling in the data and you're parking the file into a data frame. And for online storage, you have a Redis cluster or where you can have your data stored into a Redis data frame.
But from understanding, if you are serving the model, which you don't need this historical data, right?
No. We don't need historical data. That's why for serving the data, you can have an online storage data. But for here, in this example I just showed, you can have a batch data, but you can have just a online data also just to have, just where is this, yeah. So you have to just pull out this client.get online features, which will quickly, with a low latency, with a minimum time, it will pull out the data and we can predict it on top of that. You have to rearrange the data with respect to that. And once you rearrange, you just hit the endpoint. So we don't need historical data for serving. Historical data is only for training. Online data, which is retrieving via Redis, you have to predict it with your model serving either Ben2ML or serving any endpoint of yours.
But I have also another question is like,
okay,
let's say we put the data in the Delta table, right? Then compared to this feature store, I really did not see lots of benefit comes from this feature store.
So feature store, like if you see on the high level, right? I say in the domain perspective, you have a features, right? What you will do with this features? Now you have a data, raw data. Some might doesn't know about the domain perspective, right? Some might doesn't know about what is that things going on in the data perspective. Now you as expert, you have transformed your data features. Now it will not do a feature engine step. It will save your features as a central repository, and with minimal time, it will give you a pull out the data. Let's say I want the data. Let's say X data scientist is there who have transformed the data and saving it into a CSV file. And another data, any SQL or any other location. Another person is there which is train the data or model the data or pre-process the data and is saving into a Y file. Now, two data scientists have saved the data into various formats and various things or various analogy in various locations. Now, it's very difficult for them to share across the data now for modeling perspective. Now, you have a central repository. All you need to call a central repository ID registry where you can get the feature store data and it can come up quickly and you can train the data. With respect to domain knowledge, at that perspective, features store will come into the benefit for different model data, for different industries, for different perspectives. So that's where the feature store comes, and for serving endpoint, for low latency serving, where you can get the data very high memory structure in a Redis data clusters. I hope you.
All right, thank you.
Cool.
Aniruddha, another question. Here, you have used KF pipeline, like I think it is lightweighted component, right? What is the efficient way to write a Kubeflow pipeline? Like whether a lightweight component is mostly used, or let's say I'll say like one example, like from data ingestion to model serving. Like data ingestion, if I write a file, data ingestion.py, data prep.py, like model train.py, evaluate.py, and serving.py. So on the top of those files, if I create like in Kubeflow, we have container option. Is that better way to execute the pipeline, or like lightweight component is a better way?
I think lightweight company is better way. I mean, if I feel like it depends on yours, right? If you want to have a Ubuntu image, or if you want to have a your custom image of Python or Node.js or any other things, you can build your own. Now, lightweight, or you can, let's say you have a heavy image, your image is very too heavy, right? On that perspective, you can attach CPU, a good amount of CPU on the backend for the particular amount of time. Let's say you are training a data and your image is very heavy. You are using a GP3 model or any other heavy model of machine learning. For that perspective, you can attach a CPU or a machine resources on the backend, which will train the particular set of a component or a container of the particular frame of time. But I will prefer lightweight and attach a CPU with high machine. That's it. Your work will be done.
Okay.
And sorry to jump in. I just have to jump off for another workshop, but the Zoom room is open for you to keep answering the questions. All right. Thank you so much. Bye.
Thank you. Do any have any questions?
Aniruddha, this is Raj. I have one question. So when we're using this feast, right, for the feature store, does it provide any additional capabilities to find the drift in the features data in the production?
No. So that's why I mentioned, right, in the what feeds not provide. So drift, that will be a different model thing, right? You have to have your custom model drift technologies. You have to integrate it. Feast is only for the stuff. Yep.
Okay. So Kubeflow has any additional components to encounter this issue?
For model drift, Kubeflow don't have, but all is just the pipeline, right? Kubeflow is orchestrator, which will create a pipeline. You can have a Jupyter notebook, you can have your hyperparameter tunings. Model drift is not there, but you can have a model artifacts, like what is the at what time you have trained the model, and what is the accuracy, and you can build a custom drift from that model API from Kubeflow on the backend. That is a separate thing. But model drift, that things I think is not still not there. I think it's there in MLflow. I mean, it's still not there. I think.
Okay, thanks.
Cool. Anyone have any questions?
Hello, you mentioned model drift. I'm just wondering if you can recommend any open source tool to monitor the model drift.
Yep. So I think there are tools still not. I think I have to check on the tools, but on the model drift, I think you can have your custom model drift by DVC and Seams. Now you can build that model drift by your custom model governance. We can say as a whole analogy behind your model drift, which you can build it on your own, or you can use the managed services of few companies. I think Data Robot is there, and Data EGU is there. So those companies are, I think, working on that, their model dashboard monitoring management, where you can have your drift things and all. Or you can build your own model drift, or you can create custom codes. You can build some APIs and artifacts. You take the artifacts from MLflow or Kubeflow and things, and you can build that things on top of your own UI layer. That also can do.
Yeah, can I add some point like about model drift? Like for Jack, actually Sheldon is providing model drift kind of thing. Yeah, Sheldon Alibi. I think they are providing model drift. Yeah. And model explanation is also they are giving. I think almost every model metrics they are providing. It is open source. Okay.
Yeah, one more thing I have to add another point. Model drift is there in cave serving, not on the Kubeflow. I mean, the cave serving is have model drift explainer there. So you can have a look into the model drift and explainer in Sheldon, and these serving actually the serving things are there. Both Sheldon and cave serving have model drift actually. Sorry, my bad. I missed that point.
Okay, thank you. So this Sheldon, can we use this outside the Kubernetes, or it's restricted within the Kubernetes cluster?
Sheldon, we can use it, but you have to deploy it somewhere. You can use it also, but Sheldon is majorly oriented towards Kubernetes only. I think this Sheldon very tightly coupled with Kubernetes. You can deploy your own, you can scale it. So on the backend, you can use cave serving also. But a lot of people are not using Sheldon. A lot of people using cave serving, a lot using BentML, using TL serving. All depends on the person to person. Some using fast API also. I saw a lot of people are using fast API, deploying that into a fast API as a microservices for that.
Mm-hmm.
Aniruddha, like, what is your suggestion? We have to go for this serving kind of like bento ML, or creating API and creating scaling on top of the Kubernetes is better option, or so like what is the industry practices now?
I think the industry practices, if you see, the scaling is not required, right? If
Yeah.
you say I have billions of customers is there and they're hitting the single endpoint, I think at that time your application simply die. So at that time, I think cave serving provides that you can have a multiple threads of scaling on top of Kubernetes, which will scale, and you can have a canary rollout also. Let's say, and
Yes.
January I have deployed a model. In June, my first model is not performing good. So there is a model decay in this particular 6 months of frame. So on
Yeah.
that perspective, also you can scale your traffic in cave serving. Not only auto scale, you can canary rollout is there. You can auto scale you can have a security layer also. So I think I'm using cave serving. I like the cave serving, and it's all the requirements on the performance which is cave serving is really good actually with respect to KNT and Sheldon.
Okay, that's great.
Cool. Do you have any questions, guys? Cool. I think if we don't have any questions, then we can jump to other things. Thanks, guys. Then I think if we can reach out to me at LinkedIn, right? I think if we have any other things, we can discuss and on that about that. Cool.
Yeah, thanks, Andrew. Thanks for your
Okay.
session.
Thank you, guys. Take care.